Welcome. This is a recorded session of the Post-Quantum Cryptography Conference of the pKCee Consortium, which took place in Kuala Lumpur, Malaysia. This conference is made possible through the support of the pKCee Consortium Post-Quantum Cryptography Working Group and our sponsors SSL.com, Entrust, Keyfactor, HID, and Crypto4A. And with exceptional organizational support from SSL.com, Keyfactor, Logius, POS Digicert, Baker Tilly, MSC Trustgate, and Digitaurus. Join the discussion. Join the pKCee Consortium. Go to pkic.org/join.
Welcome back from the break. This is the final stretch. Well done for making it this far. I hope everybody had ice creams in the break. I will be a host and moderator for this next session, which I'm looking forward to. And without further ado, I think I'd like to just welcome Teik Guan up onto the stage. He is the founder and CEO of a very aptly named startup called pQCee with double E. So he's in the right place. Obviously, so please, everybody, join me in a welcome of Teik Guan onto the stage. Thank you.
Thank you, Jonathan. So I was just commenting during the break that this is almost more than half my logo already. I just add 2 E's there and life is good, right? So hi, good afternoon, everyone. My name is Teik Guan from pQCee. And I'm here to share about our journey when implementing a product, which is a quantum-safe encrypted email. So it is a product for us, but I'm not here to sell that product. I'm here literally to share with you some of the issues we faced and what are the things we did to overcome some of that and eventually got to where we want to go. So please, I do welcome lots of questions. Whatever that you want, please ask. One background slide about pQCee. We are a startup from Singapore. Myself and Che, we are the co-founders of the company, 3-year-old company, still very small. The reason why we got into this encrypted email thing was because we were doing a grant with the Singapore government. They wanted us to integrate the whole pKCee solution, do S/MIME, email stuff, and we realized we were facing so much issues that we had to do a lot of tweaks along the way and got to where we want to go. So it's about sharing that stuff again. Let's just go straight into it. So I guess I do not need to really repeat about whole data under threat. We understand that. That's why all of you are here. What is different is that some of the customers we talk to say, I have so much data, where do I even start? And in fact, the way to start is data that can be easily harvested. That's just a simple way, right? I mean, we have data that's in the back, behind 3 firewalls. Chances of that being harvested, probably not as easy as a web application that you have users that comes through the browser using the hotel Wi-Fi, and then you get all that data that's harvested. So web applications, internet banking, tax reporting, file transfers, e-citizen portals, one very easy way to get harvested data. Second one, VPN connections. Lots of VPNs, site to site, branch to HQ, remote offices. Again, that's another area where lots of guys like to harvest data. All I need to do, I change the BGP, all the data comes through me, I harvest it. Third area, application level, right? Documents, how are your documents being sent? Emails, APIs, file transfers. These are the ones that, again, have been the target for Harvest Now, Decrypt Later, because they literally know what this application means, they literally know what the files represent, and if I can harvest some of this, makes a lot of sense. So instead of trying to figure out data encryption, on a broad blanket basis, what we wanted to do now is to focus on even just data that really goes over the internet, data that's easily harvested, and let's go focus on how to protect those. And for those who do not understand Harvest Now, Decrypt Later, I know none of you have fallen into this, but I did this in my slide, so I'm not going to take it away. I'm going to do a very simple flow of what Harvest Now, Decrypt Later happens, right? So Alice and Bob, in every cryptographic presentation, we need to include Alice and Bob. Alice is sending a message to Bob. Alice uses Bob's public key to encrypt data, and Bob uses his private key to decrypt that data. That's easy. We could be using, classical algorithms like RSA or ECC. And here comes Eve. Eve, being the eavesdropper, what does she do? She simply collects the information. She collects the encrypted information, she stores it. The downside for her, she's going to store petabytes of data. It probably costs some amount of money, maybe not a lot depending on the ROI, but she's going to collect a lot of data. And when a CRQC, a cryptographically relevant quantum computer comes, Eve is going to take the public key, Bob's public key, calculate Bob's private key, and decrypt the data, and then do bad things with the data. Sell it, ransomware, blackmail, whatever you can imagine, right? So that's harvest now, decrypt later, in a very straightforward way. I mean, are we there yet? Not yet. We are at step 1. We are waiting for step 2 to happen. We hope step 2 may or may not happen. We hope that we're ready before step 2 really kicks in. So, and what we wanted to do then is, emails are a real big, a big information repository of lots of valuable stuff. I mean, besides just your regular emails within your employees, you send a lot of stuff to your suppliers, to your customers. I know of many SMEs that literally use their email as the repository for all their data. That if you shut down their email system, they literally lose their entire company's history of data. So everything is in that email itself. And if this email therefore gets compromised or gets harvested, we have a problem. The traditional way to do secure email is using pKCee. And I know I'm in a pKCee consortium. I know we're supposed to do pKCee, but surprise, surprise, we do not use pKCee in our encrypted email. I'll explain a bit more, but the difference between what we are doing versus what we realize needs to be done is quite different. If you use a pKCee to issue keys and certificates to everyone, you use S/MIME as the format, and we know that, and Thomas has shared earlier that the post-quantum pQCee standard for S/MIME has just been confirmed as well. We could technically use S/MIME, but when trying to implement it at the user level, we were working on Windows. We realized that we had to get S/MIME working. We had to update the CSPs, the CNGs, in order to support MLDSA and MLKEM. And that was a nightmare. We were trying to get it, we tried to push it into Microsoft CA, and oh my God, that just took so long. So that was an issue, first. Secondly, how about sending emails to external parties, right, outside the organization? Does it mean that we also have to issue keys and certificates to those guys? That, again, not so much a technology issue, but really a logistically issue, right? I mean, banks are currently sending emails to their customers on a monthly basis, updating them about their monthly bank statements and their reports and their transactions and investments. And they don't use S/MIME. What do? They encrypt that PDF with a weird combination of your ID and your birth date and your mobile number and some weird form, and think that that's secure. And that seems to be like the state of the art in many, many parts of the world, including Malaysia, including Singapore as well. So just doesn't sound correct. It just really, really doesn't sound correct that in this day and age where we have so much technology that we want to move from classical security to post-quantum security, we still are relying on known answered passwords to encrypt very sensitive information, very personal information from regulated industries like banks to their users itself. It's mind-boggling. And that was what was really, really irritating us. And therefore the team said, we need to do something that could bypass some of the pKCee challenges, but also be able to support a B2B or even a C2C kind of a usage in email, in encrypted email. So we then started to sit down and say, what are the use cases we could do? External reporting, I just gave the example, banks sending documents. Well, it's not just banks, right? I mean, insurance, many of the other industries, even in defense or the military, they have contractors, they have civilian contractors that they do send information. They have users, and if these users are not part of the organization, what do? How are they sending their emails? We started to discover a lot of weird practices when trying to do security through obscurity rather than real proper cryptographic security. Second is really about privacy as well. Quite often, users are asked to send privacy information, please scan your passport and email it to our admin itself. Do I just send it? Is TLS sufficient? Can we do more than that? Well, the user has no control over it. And then the third, which was a very curious thing, was about onboarding. You have employees coming in, and then when the employee needs to come in, he or she has a first password in order to log in as a one-time thing. And that one-time password, surprise, surprise, is sent in the clear to an email address. Is that the right thing to do? I mean, we can do more than that. So we started to realize that there are a lot of use cases for encrypted email from a B to C kind of approach, or a C to C kind of approach. And that's how we started to build and get onto it. So we sort of nailed it down to three broad requirements. One, as a post-quantum company, it must be secure against harvest now, decrypt later, right? So bear in mind, we're talking about encrypted emails. We're not talking about signing, we're not talking about non-repudiation, just harvest now, decrypt later, which is an encryption thing. Two, minimal key management. So we don't want the silly, but the practice of using a combination of your ID plus your birthday plus your handphone number and your mother's maiden name in order to encrypt some document. No, we don't want that. We also don't want to have to send public-private keys to each other when you're trying to send millions of emails out there. Because if we're talking about crypto agility, that's not going to work. That's not going to work if you're going to send keys to everyone out there. That's not crypto agility at all. And third, this was something that we added in, was that, in the face of AI, and we did see some questions of AI, are the mail providers, I mean, I'm not saying who they are, but are the mail providers actually mining our data? Are they mining our emails? Are they reading them? Are they doing stuff that we didn't allow them to do, but they still do it? Can we actually stop them from doing it? So we want to make sure that data is really end-to-end encrypted, regardless whether in between whether your TLS is upgraded, good for you or not, or that the data that is stored or data in storage on the mail server must remain post-quantum encrypted. So these were the three requirements that we set for ourselves, and I will then share what we did for each other. So requirement one, secure against harvest now, decrypt later. Now this is the easiest way to answer it. Use MLKEM, right? So we know this. This came from the NIST FIPS 203 document itself. I didn't draw this, came from there. And it's MLKEM. So if we use MLKEM, life is good. We have a public key, we have a encapsulation key, which is your public key, and the decap key, which is the private key. If data is encrypted with the encap key and decrypted with the decap key, life is good. We know that it is secure. We know that it is quantum safe. So implementing post-quantum encryption was definitely the first step we did. And then we started looking into what can we do about it. We focused on the email body itself. So if you look at emails, there is the recipients, there is the subject, and then there's the email body and the attachments. We focused on the message body and the attachments. We wanted to just encrypt that, similar to what we do for PGP, while keeping the recipients and the subject intact. So the recipients and the subject were left intact because those were used mainly and could get into the whole, didn't get into the problems of all the DLP protections that you had. It didn't go into the spam mail and had the interoperability that could allow the email routing to do. So we focused on just the message body and the attachments at which we wanted it encrypted. How do you do the encryption? Simple, right? When you send an email, when the user clicks the send button, we take the message body and the attachments, and then we encrypt it with MLKEM, and we replace that content onto the message body. Not rocket science, okay? So this is a simple first step that we did. The next one comes a bit more complicated. The next one is about key management. Bear in mind, I said we didn't want to use public-private keys and be able to send keys. A big part of S-MIME was about relying on the recipient with a private key to be able to authenticate to the email system in order to decrypt the information. Now, we are missing this authentication piece. by just simply using MLKEM, you do not have authentication. You have encryption, you do not have authentication. So what did we have to do? In order to achieve this minimal key management, we had to rely, therefore, on an external authentication source. In this case here, the most convenient one was essentially the email provider. We needed to know that for someone who wants to decrypt the information, that he or she is the rightful recipient of the encrypted email. So if we could verify the ID of this person wanting to open that email, and we know that it comes from a trusted source, for example, the email provider, and rely on OAuth single sign-on authentication itself, then we would have sort of solved the authentication piece. Right? So it is not a pKCee authentication, but it is basically an OAuth authentication that we do before the email gets opened up. Right? So we've replaced the private key storage of the recipient with the OAuth token authentication. It's still a secret, but a secret that was issued by the email provider in order to authenticate this user when trying to decrypt and view the email itself. Right? So that was the first thing that we did that was really different from your regular S/MIME implementation. And that really made things open up a lot, because what we could do then is start to interface with a lot of different emails. We managed with this to interface then with Office 365 and also G Suite, Google, right? So, and that became there because they were running OAuth systems as well. They were doing so much single sign-on and authentication that we just connected to their authentication system. Oh, we could verify their IDs. And there would be other email IDs that will come along the way. That is a backend integration, but that's a one-time effort to do the integration. But immediately from an end user perspective, we no longer needed to have the birthday password and all that stuff inside there. We also didn't need to give keys to that recipient. So that was a way to give us the ability to scale. And then the third requirement, any questions so far? Am I going too fast, too slow? You guys are lost? Okay. So the third requirement was something that's a bit more interesting. So data leak. We wanted end-to-end encryption. Right? So now you're wondering now, oh, where are the keys? How are we going to do this whole thing? And we wanted, on the other hand, to ensure that the email provider would never be able to decrypt that information. So we wanted end-to-end encryption of the email, that only when email is sent, the email is encrypted, that only when the email is viewed at the end user, the email is decrypted, and never anywhere along the way. Right? This is end-to-end encryption. It is not TLS. I mean, it's not dependent on TLS. That means that along the way, that you could have a TLS that's 1.2, 1.0, 1.3, whatever. That's still fine because we are encrypting data at layer 7. So we had to implement then end-to-end encryption at the front end. And one thing we discovered was that literally all our front-end devices were browsers. Even though it may not look like a browser, it's a browser. If you use your Outlook Classic, if you use your new Outlook interface, they literally have a JavaScript and a browser interface inside there. They're literally a browser engine inside there. All your mobile apps that you use, they're all browsers inside there. And so one thing that was common across all of it was JavaScript. If you therefore had JavaScript that's here and the JavaScript that's here, both on the client and server, on the sender and receiver, then you literally can perform encryption and decryption at the client side if you sorted out the whole key management properly. And that was what we discovered as well, that literally just using JavaScript for encryption, for keygen, encryption, decryption at the client side worked. And therefore, we wanted to make sure that all of these is done through a proper key management in place and get it done. So I've sort of drawn this picture here where we first had a backend. Also, we do have to have a key manager in the backend. We ran this on the Azure on the Azure system on the confidential compute, where we implemented a TEE module, and this did the key generation. So what happened? We generated keys in the backend. We gave the public key to the sender, and then when the receiver wants to view it, we can then provide the decryption key, and life is good. We had to sort out the other end-to-end stuff in place, but that was the basic principle of how we designed it. So we just used one, MLKEM, two, single sign-on for authentication, and three, a central key management that handle key generation, key generation and key management, and that was really how we put in place the whole encrypted system. Right, so for the sender, we use MLKEM encapsulation. We used 768 because that seemed to be the right thing to do. The great thing about using JavaScript was that we could also then change it to 1024 or even HQC by just replacing the JavaScript libraries, which were never installed in the first place, right? So they're downloaded and dynamic. So it gave us the whole crypto agility part. Never tested, but the design seemed like we could get crypto agility out of it. But we could simply encrypt data on the client side from the sender and only decrypt it on the receiver end. And everything else, regardless whether you are using obsoleted devices or stuff that's not been upgraded or post-quantum, you are still fine because your email is already end-to-end encrypted. So that's really what we did in order to get there. I'm going to put it together to explain the whole flow. So this is literally the architecture of what we did. Nothing rocket science. I've sort of run through with you. If you look at the sender, who is number one, so you create, and I was supposed to do a live demo, and then I realized I couldn't do it. So if you want to see a live demo, we'll show it later. But I'm not trying to sell you this stuff. I'm just trying to show you how the flow works. So sender composes the email in Outlook, or browser, or whatever that you want. You create the email, and we have an add-in. This add-in, upon clicking the send button, this add-in talks to the TEE service to ask for a public-private key pair. He gets the public key, he encrypts the data, and then he sends it out. Sender does not need to know what is the receiver's key because there isn't a receiver key. He just sends it out. Sender may not have met the receiver for any time, but as long as the receiver is in the recipient list, that person can decrypt it. So it's sent out, number 3 goes out, email provider by the sender, email provider by receiver, gets an encrypted block, cannot do anything about it, simply transfers it forward. At the receiver end then has also an add-in that will first authenticate, that will send a request to the TEE service with the email token of the email ID token to the TEE. The TEE service authenticates the token against the email provider, gets a yes, checks that the email ID belongs to the recipient list, and if it is, gets the decryption key. And then the receiver can decrypt it. So we've sort of separated two things, right? One, the email provider, which contains the encrypted email, does not get the key. This TEE service that handles the key does not get the email. So we've sort of also separated that and achieved that purpose while achieving end-to-end encryption across this whole platform. Right? So that's really the broad area of how we implemented it. I mean, the challenge was not the cryptography. I need to tell you, the challenge was not cryptography. The biggest challenges were trying to interface into Outlook. If you tried to write JavaScript in Outlook Classic or Outlook New, and you start to realize that every few months, something breaks. Because someone upgraded something, no one tells you about it, it's not documented on Microsoft, but something breaks. And you then scramble to go fix your JavaScript to get it working. That was really the pain that we had. So in fact, before this presentation, it was working on my phone. It was working on my phone. And today, it broke on my phone. So it's good that I don't have to do a live demo for you. That's the kind of pain we had. So it was mainly user interface, right? I mean, most users expect you click a button and it will work. We spend a lot of time, tweaking the JavaScript for it to work with both Office 365 and Gmail. I hope my